but I know that people are actually looking at the lectures. And if you have any comments or questions after looking at the video of the lectures, please send them to me. I want to get as much feedback as possible from you. So we continue our discussion of what we call Bayesian decision theory. And I just want to recap quickly what we said, the main thing we said so far. So we're talking essentially about a setting which will continue in our course many, many times in more and more elaborated way, and I really want you to get it. So we have some sort of a world, which can be a real world or some sort of a made-up world or whatever you want to think about it. It's or some sort of reduced real world, which actually sends us observations. I mean, so we see some random variables from the world. So there's some sort of what we are going to call channel later on. I mean, some sort of probability distribution that connects our observations. So this is observations. And there's usually some sort of distribution here. So there are states of the world that we call omega or x, and there are observations that belong to some general multivariable x, and there are some actions that we are going to take as a function of the observations. So observations, world, in a very general sense, and actions. And so there are some actions that belong to some set A, which we want to decide upon. And Noga noted to me that this kind of a Markov chain, I mean, the connection between the world, the observations, and then the action is going to be useful as a general framework for what we do. So there's some channel here, which we're going to call eventually, I denoted it by pi, the probability of an action given an observation. So this is really a Markov chain in some sense. The actions are depending on the observation, which depends on the probability, and there's some prior distribution over the world, which we assume is given. Okay? So you can think about it as some sort of Markov process, and if you know what the Markov process is, so this depends, the actions depend on the state of the world only through the observations itself. So this type of a channel chain, we're going to generalize this picture later on to be much more interesting. So it's very simple so far. And of course, the assumption here at this point that the world is fixed, the states of the world are given, we know what they are, and we see some observations which, as I said, can be noisy or can be incomplete. And so this is, and then we have to make a decision. So we have here essentially this formal structure: world, observations, action, and then we quantify them, the quality of our decisions, by something which we call the cost or value or utility or reward. There are many, many different names that you can find in the literature for this type of quantities, but they are not what we call the cost or the price matrix. Lambda, in general, it's a lambda which depends on our actions and on the state of the world. Okay, so this is in general a function of two variables, but I want to think about it as a conditional function of conditional state of the world. And of course, part of this model, the Bayesian decision model, is that we have those probability distributions. We call this curly P, which are made out of two things: the prior over the state of the world and the conditional probability of the distributions on the state of the world. So these two entities, the conditional distributions and the prior, are part of what we call the statistical description of the problem. And what we are looking for, so this is the formal objects in this is the model, if you want. The model, of course, includes also the specification of the states and the observations and so on. This is statistical model, and there's something which we want to find, which is our strategy, how to make the decision, which I said, in general, we'll think about it as a distribution. But in the context of what we do now, it's enough to think about deterministic functions of the observations, which we call decision rules, where the delta is a function from the observations to the action. So what I mean by this, it can be a stochastic function in principle. But right now, as you're going to show yourself in the exercise, or it showed already, a stochastic decision is not going to help us much. It's not going to reduce the risk. Okay, so these are the entities, the formal entities that define our problem. And we actually showed that the optimal strategy or decision function, the optimal delta, so optimal base and decision is the function, is specific function. So for any observation, any x that we see, what was it? It was the action that minimizes the conditional risk. Okay? So it was the arg min of all possible actions of something which I call the conditional risk, or we call conditional risk of alpha given x. So this and how did I define this conditional risk? So this conditional risk was when r alpha given x was some sort of an expectation over the unknown in this case, which was the state of the world. So it was the sum over all the states of the world. We don't know what the state of the world is, so we average over it. Of what? Of the cost of alpha at this state of the world times the probability of the state of the world given the observation. Okay, so this is very simple. Okay, very simple, very intuitive. And of course, this probability of the state of the world given the action, notice here that if something is unknown, we can always condition on it and then average. So we have this, of course, the assumption here is that omega is exhaustive in the sum over all possible states of the world, and the states of the world are disjoint. I mean, we cannot be together in two states of the world. Okay? So always in one of them, never in two of them. Okay? So, and of course, we use Bayes' rule from Bayes. This is why the whole thing is called Bayesian. We can always calculate this as the probability of the state of the world times the probability of observation, condition on the state of the world, or the likelihood of the observation, divided by P of x. And we can always write it as using the complete or total probability formula as simply a normalizing factor. So this is the sum over all omega of P of omega, P of x given omega. Okay? Just to make it clear, this is the dummy index here. So I've denoted it by omega prime. Okay? So essentially, plugging this here, we know how to calculate the conditional risk from the model. Nothing is undefined here. And then we can actually prove, was a very simple theorem. So we have this. We have this theorem that if we define the total risk, I should do it here. So what was the total risk or the expected risk? So the theorem was that the total risk of the Bayesian decision rule is minimal, is smaller or equal than the decision rule of any other decision rule, actually either deterministic or stochastic, where delta is any other rule, function, stochastic, any other rule, and where R of delta was what? Was the expected over X, expectation over probability of all the observations of the conditional risk, or actually plug in the observation, the action that I said. Okay, so this is what we showed last time. Any questions about it so far? This is really important. And so this is the justification that the Bayesian decision really is the best we can do in expectation. As you saw in the exercise, or we'll see, there are many the other criteria like min-max or other ways of defining the best. Min-max is we want to minimize the error in the worst possible case. This is something which is often used or almost always used in game theory or in economy and other things. In our cases, the maximum, the worst case can be very bad. I mean, if you're talking about really a big world and many, many possible observations, so on, the worst case can be something which you cannot control. So min-max is actually asking too much in many, many cases. So the best thing to do, and it's going to be our strategy all along, is to minimize the expectation. But notice that minimizing the expectation doesn't mean that in very specific case we cannot do a very, very bad thing, as long as this happens with small probability. All right. So if you don't have any questions about this, we then took a special case, which we call sometimes simple decisions, or in a different context in statistics called hypothesis testing, where there are only two states and two actions, and everything is very simple. In some sense, it's very much like this example of rain and umbrella, two states, two actions. So what we call binary decision, in the case of simple or binary decisions. So what we mean then is that both the world, as far as we are concerned, omega, is made out of two states, or if you can think about it as a union of two disjoint set, or something like this, where we want to decide only if we are in this set or in this set. And A is only two actions, alpha 1 and alpha 2, which in the context of hypothesis testing we usually call accepting the null hypothesis or rejecting the null. And we'll say it in a minute more formally. And in this case, the matrix lambda, alpha omega, is just a 2-by-2 matrix. Okay, so it's a 2-by-2 matrix. You can just write lambda 1 1, lambda 2 1, lambda 1 2, and lambda 2 2. Okay, and in this case, so this is the constant price matrix, and then the condition of minimal risk. So the optimal base decision, or the base optimal rule, will simply compare our alpha conditioned on X, alpha 1 condition on X, compare it. I'll write it like this. I hope it's not very confusing. What I mean by this, decide this if this is smaller, decide this if the other one is smaller. Okay? We have to compare these two things. Okay? And this is going to determine our decision regions. I mean, where in X we're going to decide alpha 1 and where in X we're going to decide alpha 2. So this defines some sort of partition of X into regions where we, for each X we take the smaller one and decide the given the alpha accordingly. And in this particular case, it gave us actually a very nice rule. Not going to repeat it. It gave us the rule that what we have to do is to look at what we call the likelihood ratio. And compare it to a number which is independent of the observations, which was what? Was a ratio of the two priors. After I use Bayes' rule, times some function of the matrix of the prices. It was lambda 2, 1 minus lambda 2, 2 divided by lambda 1, 2 minus lambda 1, 1. So this was our decision rule. This is a very simple thing to see it from this. Okay. So I looked at this and said, okay, this is very nice. Essentially, what you have to do here is compare the ratio of the two probabilities, which from now on we're going to call the likelihood ratio. Likelihood ratio. It's a very important notion or concept of these two things. And compare them to something which is essentially independent of observation, depend only on the priors and the costs. So it's some sort of threshold, denoted by theta. Compare it to some threshold. And this is going to determine our decision rule. And we also say something interesting in the special case that our alpha is essentially deciding about omega. So if you want, alpha 1 is decided the state is in omega 1, and alpha 2 is decided the state is omega 2. So alpha and omega are essentially isomorphic. I mean, it's a decision about the real. A very natural thing to do is to look at lambda ij as 1 minus delta ij. In this case, I and j goes from 1 and 0, so delta ij is what we usually call the chronicle delta. It's 1 in I is I if I equal j, and 0 if I is different from j. Okay, so it's, if you want, the unit matrix and delta ij. And in this case, we saw actually, maybe not very clearly, but I want to just emphasize it again, that in this case, okay, so what's going to be this ratio in this case? Yeah, just 1. So it's going to be minus 1 divided by 1 is minus 1 if you want. Just 1. And essentially, in this case, this just falls out. And in this case, the total risk, so in this case, the decision rule is just compare the likelihood ratio to the prior ratio. And the total risk this one of the Bayesian and of the optimal total risk, or the Bayes optimal of delta V, the Bayes optimal decision rule, was what? So this is something I actually wanted you to verify. I said it very quickly last time. So the total risk in this case is simply P omega 1 times the expectation over P of X in the region that alpha 1. So we decided alpha 2, and this was actually alpha 1. So it's in the region where the probability P omega 1 Px over omega 1 was smaller than P omega 2 and Px over omega 2. Of what? So I made this decision and actually decided this was actually smaller than that, but the error I made was actually P omega 2. Plus, this is omega 1 here, I'm sorry. So this was P omega 1 times the probability of omega 1 that I decided 2. Or alpha, I call it alpha was alpha 2, simply. Plus P of omega 2, that's the expectation of this, alpha was alpha 1 of P of x. This was omega 1, and this is P of x, omega 2. And these two things are simply the tails of the distributions. So this, I got this just for plugging here the Bayes rule here. This one in here, and looked where I decide. So I always decide, because of this minus sign here, I always decide on the lower probability. So the lower risk is going to be at the higher probability. And what we got here, these are the two error probabilities. So this is the combined error probability. There's a probability of wrongly deciding 2, or wrongly deciding 1. I mean, we were at 2, wrongly deciding 2, and this is wrongly decided 1. So this is simply the average error. We're going to call alpha 1 eventually, delta, of probability of false acceptance. Plus probability of the second one of false rejection. These terminologies actually belong to hypothesis testing, but it's the same thing. Or what we call false positive and false negative. I'll show this in a minute. Okay, so this is something I wanted you to play with. And so what we got in this particular case, if we take this particular cost function, the risk is simply a sum of two weighted errors. If you remember in the Bayesian case, this was essentially a relatively simple thing to. If this is the optimal decision, and let's say the priors, let's for simplicity assume that they're equal. So this was one error, one type of error, and this was the other one. Probability that you actually decide something, but we were in the different state of the world. Okay. So now I want to extend it just slightly and talk about, I just want to make sure that I didn't miss something I wanted to say. Yes, okay, good. So I just want to mention the same thing essentially in this language of statistics, which is known as hypothesis testing. So in statistics, maybe the most important thing that statisticians do, and actually I will actually argue later on that this is actually the most important thing that the brain is doing as well, is what we call hypothesis testing. So hypothesis is actually a very special case of what we just discussed. So what is hypothesis testing? Some of you have seen it before. I guess all of those who actually learn statistics in psychology or cognitive science, or in medicine or in any other field, this is what we usually do in statistics. I mean, we have to decide between two alternative hypotheses or complementary hypotheses. So in this case, we call the null hypothesis null. It's really just an historical name. Hypothesis, call it H0. So we actually assume that omega in this case is made out of two disjoint sets that we call omega 0 and omega 1. And H0 is accept that we are in omega 1, or accept the null hypothesis. And the alternative is what we call H1. This belongs to omega belongs to omega 0. H1 is omega doesn't belong to omega 0, or if you want, omega belongs Omega belongs to omega 1. Okay, so it's really the same thing exactly, just the names are different. But then we make this just a little confusing terminology again. We call these two errors type 1 and type 2 errors. So again, this is something which I'm always confusing. So what we call type 1 error, and we denote it by alpha, or sometimes to confuse us, we denote it by alpha again, but I'm going to use the standard notation here. So this is in statistics, they usually call it the significance level, or say how significant is your decision. I mean, this is the probability of error of type 1, which is what? So if we have I just want to make sure that I'm not mixing it. So if we have a decision rule, it's the type 1 probability of this decision rule, and this is what we call false positive. So if it's false positive, it means that we actually decided H0 and we're wrong. Okay? So we positive means so this is a positive decision, positive test, and this is a negative. Okay? I mean, it's other than confusing terminology, there's nothing new here. And of course, type 2 error. Well, I don't know. I mean, this is depends. Another hypothesis is what you want to test. Okay. I mean, if you accept it, then it's positive test. If you reject it, it's a negative test. Okay. What exactly you call a null hypothesis and the alternative hypothesis depends on your context. So, for example, in the case of testing a medicine, so my hypothesis that this medicine is actually working is usually the null hypothesis. If it's actually, I think it's working, but it's not, it's a false positive. And the type 2 error, usually denoted by beta of delta, is what we call false reject. False negative. So this is false acceptance, and this is false reject. Okay, this is false acceptance. This is usually called, alpha is usually called significance level. And beta, how's it called? It's actually usually 1 minus beta. It's usually called the power of the test. Again, just to confuse it. So 1 minus beta is the power. Now, it's actually interesting because since most people really, when they do hypothesis testing or when they do machine learning or they do anything, they usually like to plot things in these two terms, power and significance, in terms of what we call ROC curve and things like this. You'll see it in more detail in the exercise. I'm always confused by that. So but this is the standard way of thinking about the power of the test. Okay, so this is a simple renotation of what we call simple hypothesis testing, or simple decision. But it's so standard and so important that you have to know that. And the main statement here, which is going to be essentially trivial for us, but it was not trivial when it was proved, is what people call the Neyman-Pearson lemma. So there's a theorem, or a lemma if you want. Which is going to be essentially a simple exercise for us now. So in the Bayesian setting, so the lemma, if you all know what lemma is, it's what mathematicians used to call a simple theorem, or something that helps you. Sometimes these lemmas are very deep and very non-simple. Usually, sometimes they contain the main difficulty of the problem, but they're not exactly what you wanted to show. So we call it lemma, Shpat Ezer or something like this. Okay, so this goes all the way to Neyman and Pearson. two very famous statisticians. We're actually going to see their names again and again in a few other places. Neyman and Pearson, and this was proved in 1933. Before the Bayesian framework was really well accepted everywhere. But it's not. So they actually proved it in this particular context, and what they showed that the ratio, so what we call the likelihood ratio test. So I'll define something which I call the likelihood ratio of a sample of many observations. Let's call it later on something, or dimension many observations. In this case, it's not really important. You can think about it just as X. As I said, the likelihood ratio test. The likelihood of the observations under the first hypothesis divided by the likelihood of the observations, or in general observations, under the alternative hypothesis. And what so if we what they say that this particular likelihood ratio if you compare this to a theta threshold, so this decision rule is really compare this to some threshold. Let's call this decision rule delta of theta of X. Okay. So given a threshold theta, compare this to a threshold. So this is what we call the likelihood ratio test. Compare the likelihood ratio to a threshold. Is the optimal in the following sense that Neyman and Pearson decide. So the errors. This is really right now a very simple thing to say in the Bayesian context. So if the error, and this is sometimes called E1 and E2, okay, error 1 and error 2. So just again, so you know the notation. So the alpha of delta theta, or the E1 of delta theta, this is the error of this, and beta of delta theta, which is the E2 of delta theta, it's the same thing. If these are the errors of this particular rule, then what we have for any other, then for any other delta, any other decision rule, delta of X, what do we know? That if again, say it again, that if alpha of delta is less or equal than alpha of delta theta, this implies that beta of delta is actually worse than. In other words, this particular test is the most powerful test at a given significance. This is usually the way statisticians say it. So the Neyman and Pearson tell us that the likelihood ratio test, comparing this to a threshold, is the most powerful test at a given significance level. This is the best you can do in terms of reducing beta, or maximizing 1 minus beta, in a given alpha. Of course, this is equal or not equal. You can check yourself. So how do we? So the proof that Neyman and Pearson gave was a little more tricky. It's the same proof because they didn't want to use priors. But if we are willing to use priors, this is an immediate consequence of the Bayesian decision rule that we wrote before. So, for example, if we can choose the prior, so this is the proof if you want. It's really very simple. If we can choose the P0 of omega 0 and 1 minus P0 of omega 0, which is P of omega 1, we can choose the prior to be such that theta would be just the prior ratio. So what was the prior ratio? So it's 1 minus P of omega 0 divided by P of omega 0. Then it directly follows from what you said before. So Neyman and Pearson didn't want to talk about priors. Okay, there are no priors in the world. There are frequencies. Okay, but we can use priors. We can now invent a prior. So what we actually argue that this is precisely what we saw before about the base optimal. Okay, so the base optimal was compared to a threshold. Compared to a threshold, we assume that since we are interested in the cost, which are precisely the probabilities of errors, so we take this choice of lambda equal 1 minus delta ij. So essentially, our Bayesian optimal decision was compare the likelihood ratio to the prior ratio. Okay, so this is what I do. I just choose this threshold to be such. And then, if you want, P of omega 0 is going to be then theta divided by 1 plus theta, and P of omega 1 is just a complement. 1 divided by 1 plus theta. It's the same thing. So if we do that, yes?
Isn't there missing there is this threshold such that this is true? I mean, I don't understand
This notation?
So do you mean there exists a threshold on which this occurs?
So what I'm saying that comparing him to any threshold, comparing the likelihood ratio to any threshold is obeying this. I mean, so if you, okay, you're right. I mean, so there's it seems to be arbitrary. I mean, it's not one threshold compared to any threshold, and then in the Bayesian setting, we actually determine this threshold. Determine the optimal threshold to be, in this case, that's simply the prior ratio. So what I'm saying, okay, you gave me a freedom. I mean, Neyman and Pearson gave me the freedom of choosing the threshold, if you want, or choosing the threshold is for me precisely choosing the prior ratio. Since they didn't tell me what the priors are, I can recast it as a Bayesian decision with the right choice of priors. So it's not for a specific threshold, for any threshold. Comparing this to a threshold is the best thing for a certain significance level. So the threshold is going to determine what is your alpha. And then this particular test is going to give you the most powerful decision. And actually, it's important that you can play with the threshold. So you can, for example, do a test in psychology and decide that your significance level for which you need to publish the paper is 5%. Okay, so the probability of first-type error is only 5%. It's a very poor significance. But let's say that's what you want. So then there is a certain threshold that you need to cross in order to guarantee this 5% error, and and then minimizing the error better. And that's really important. That's not a unique threshold. There are many thresholds. I want 10%, or I want my percent. It will be a different threshold. Okay? What's her name? Susanna. Okay, just to make sure that I answer the right person. Okay, so it's actually an important question. I mean, I'm not fixing the threshold. I'm actually now just recasting it as a Bayesian decision by choosing the prior. So this is some sort of trick. I mean, I just move this into this by choosing the right priors, and then it is a Bayesian decision with this prior, an optimal Bayesian decision with this prior. Which means what? That the total risk is smaller than the total risk of any other hypothesis. So under this prior, we know, so this means that R of delta theta is what? It's the sum, the weighted sum of the two errors. Okay, so in this case, it's going to be the weighted sum, yeah, P of omega 0 times alpha of delta theta plus P of omega 1 times beta of delta of theta. This is simply the total risk, as I was more or less showing to you. But we know that this is going to be smaller or equal than the total risk of any other decision with the same priors. Okay? So this is going to be less than P of omega 0 alpha of any other delta plus P of omega 1, the beta of any other delta. Okay, so now I can just rearrange the terms here. I should write it here. So simple rearrangement just tell me what I want, essentially, that P of omega 0 times alpha of delta theta minus alpha of delta is less than P of omega 1 times beta of delta minus beta of delta theta. This is a simple rearrangement of this. Just take everything that multiplies P0 together, everything multiplies P1 together. But since P0 and P1 are non-negative, essentially it tells us that if this is positive, then this must be positive. And if this is negative, then this must be negative, which exactly means the theorem. Okay. So if I actually found something which is better in terms of alpha than delta theta, this means that this will be positive, then this will be also positive, which means it has a lower beta. So just comparing these two things. Okay? Any questions about it? So just these two things must be positive and negative together. Okay? Yes?
Like if the left hand of the equation is negative, the right hand does not have to be positive. It does not have to be negative too, right? If the left hand is negative, the right hand can be positive.
That's right. But the first part of the theorem is this: if delta, if this is positive, I mean that this is greater than this, then this must be positive. And this is enough to state the statement as it is. You're right. Forget about the negative. Negative should go in the other direction. If this is negative, then this is negative. You're right. Absolutely right. Okay, so simply by the positivity of these two things, I know that the sign, if this is negative, then this also must be negative. This is positive, this must be positive. That's enough to state the theorem. If you actually look at the statistics book, they have a slightly more elaborated proof without using the notion of priors at all. But it's essentially the same argument. So for us, this is enough. So if this is negative, then this must be negative, which means alpha of delta must be greater than alpha of delta of theta. And I can do the same with inequalities, with Greek inequalities. All right. So this is Neyman Pearson. I more or less finished my first hour. I just want to tell you just one nice consequence of that before we finish. So I want to remind you what I started to say last time, and I want to elaborate this in the next hour. So what happens if there are many observations? So for many IID observations, this likelihood ratio test has a very nice form. So the likelihood ratio of a sample is just the product I'm going back to the Bayesian notation. I just had this detour about hypothesis testing. Generally speaking, I won't talk about Bayesian world and Bayesian notation. Just want to know the difference. So I'm going back to omega 1 and omega 2, and keep this for exercises or whenever you need to talk in terms of statistical hypothesis testing. So in this case, it's a big product. What is really the sum? Where is really this IID coming in? In this, when I write it like this. So actually write each simply because p of x1 to xn, write it explicitly once, it's IID conditional on the state. Okay. So in every state, it's IID, which actually means that those samples are sampled from p of x given omega for one of the omega, any of the omegas. So it's actually what we should be very careful about it. It's conditionally independent. It's identically distributed and independent, conditioned on the state. Why is it not unconditionally independent? Okay, this is the only thing. So this is, if they are conditionally independent, means that they are drawn independently from each other at a given state of the world, and then and only then I can write it as a product. For any omega, never mind what omega is. Okay, and then of course, a ratio to product is the product of the ratios. Okay, that's what I did here. And but they're not unconditionally. But notice that p of x1, xn unconditionally. What is this? Okay, so this is unconditional, which means I have to sum over the state of the world. I don't know the state of the world. So this is sum over omega in general. In the case of 2, it's just sum over two things. P of omega times P of x conditioned on omega, which I can, xn, yeah, which I can write as a sum over omega of P of omega, a product because this is conditionally independent, okay? But this is not, I have to make sure of this, this is not the product of the unconditional. It's really not. Because I have a sum here. If you multiply the unconditional here, you get all sorts of mixed terms, which are going to make it completely wrong. So conditional independence is not unconditional independence. Remember this. This is very important. Okay, so we're going to have things, if there are things that we don't know, so things that are independent conditionally become suddenly unconditional. So this is not this. Okay, so this is just one important comment I want to make. So the next thing I'm going to do is to connect this particular likelihood ratio test before I go on to what we call multiple samples or multiple hypotheses, and then I want to go further to what we call sequential decision making. I want to actually make a little detour and talk to the neuroscientists here and show that Bayes' rule in the case of multiple observations is actually leading immediately to a model that some of you have seen, the perceptron. So the perceptron in some sense is optimal, the sigmoid perceptron, with a standard sigmoid function in the case of independent features. And so I'm going to spend 5 minutes, maybe a little more, on that, showing you the connection to the perceptron. This may be not so interesting for the computer scientists, but it's good to know anyway. Now even computer scientists are talking about neural networks, because the neural networks are back, as you all know. We have deep learning as the most successful machine learning algorithm anywhere, and deep learning is nothing but multi-layer neural network. So in some sense, we really want to understand neural networks. So what I'm going to show next is how neural networks are related to Bayesian decisions in a very simple way. And then I want to go back to what we call sequential decision. How can we make a decision if we get the observations not together, but one after the other, in some sense? So we can make a choice if to look again or not, and show how the errors is actually improving exponentially fast when we make multiple independent decisions, observations. All right, so this is the end of this hour. We convene back at 11. המושגים של ההגדרות האלה. זה כל הגדול מתטא, עכשיו אני טוען, מאוד פשוטה, אם אנחנו עושים השערה אחרת, שנותן לך שגיאה יותר נמוכה, אז לכך ומה אמרנו? עכשיו, הגדרתי את הפריימות, סתם יעשה הגדרתי את הפריימות, כמו שאני לא המשפט הזה אמר, הבאונדרי ריג'ד, וזה כפול זה, כמה מידות חייבים. אם הערך הזה, אותו בארץ, כאן אני נכון. זה בלחסון, אז זה כפול זה, קטן מזה כפול. עכשיו אני אמרתי, בוא נכתוב את הסוד ואני יודע שזה קטן שווה מהסוד תלוי שווה. זה מה שלכל היפותזה, לכל הכרעה אחרת, אם הפריור הזה, זה הדבר הכי חשוב. אז אני אמרתי, הסוד תלוי כאן, שזה השגרות של 0 כפול השגיאה, או השגרות של 1 כפול השגיאה באחד, קטנה או שווה מהתוחלת שלה.
השגיאה של האלפא והשגיאה שהיית צריך לבחור אומגה 1 ובחרת אומגה 2.
זה השגיאה הספציפית שהייתי באפס. הייתי באפס על הספות על פי אחד. אז לכל שהוא ג'ק, נכון, השתמשתי בזה. מאוד חשוב. אמרתי, אני אשתמש במה שאנחנו יודעים על זה. זה, אני יודע שזה האופן על בית במקרה הזה. ראינו שזה כל דבר אחר. ומתוך זה, שניתי סדר זה בעל משהו. אז כן, חשוב מאוד שהשתמשתי בזה. אם אתה לא רוצה להשתמש בזה, אתה יכול לעשות את זה בלי שום הנחה על פרייורים. זה קצת יותר טריקי, אתה יכול למצוא את זה בהמון מקומות. בעבר הוכחתי את זה בלי שום השערה על פרייורים. עוד שורה אחת. יכול לראות את זה למשל בקובר. גם מרחב מדגם בדיוק שאני יכול לדגום אותו.
אבל גם ה-X, אני גם מודד.
לא, X הוא פונקציה של מרחב מדגם. כלומר, X משתנה לפי אנשי, שתלוי במצב מרחב מדגם. אומגה בכלל בתורת הסתברות, זה נקרא סאמפל ספייס, בדיוק בגלל זה נקרא סאמפל ספייס.
זה ינתן אומגה, זה אומר שזה מעורב. זה מעורב.
נכון.
X הוא מעורב.
לא,
אני גם מחשב את פי של X, אני לא מחשב פי של X שווה למשהו, אני מחשב... אנחנו כותבים את הדבר הזה, פי של כמות שאני רואה את זה.
כן, לא, אבל חזרה לתורת הסתברות.
אתה אומר כאילו קצת לקרוא לזה פי של X שווה ל-X.
זה באמת הערה נכונה.
היא
מבלבלת, אמרת את זה כבר. מה בעצם אנחנו עושים?
להגיד X, הוא משתנה מקרה שיש לה את האפשרות.
מה זה משתנה מקרי? משתנה מקרי זה פונקציה ממרחב המדגם לממשי, נכון? לצורך העניין. אז משתנה מקרי זה בעצם איזושהי פונקציה מאומגה ל-R, שזה אומר אומגה, בעצם לא מאומגה, זה מכל המסתובבות המדידות בו. זה מגדיר איזושהי של אומגה, שבתוכה אני נכון, זאת אומרת, אם זה היה האומגה שלי, אז אני יכול לפרט אותו על זה באיזושהי צורה, כאן זה יקבל X1.
לא, לא, פקוד על בטא.
זה אומר ש... במרחב המדגם שלי, לכל אחד מהאזורים האלה יש הסתברות.
סבבה, זה יכול להיות בדיוק אותו דבר. פחות טוב, זה יותר טוב על זה. יכול להתעלם מזה, לא? לא, זה כאילו משהו...
עכשיו נניח ש-X מקבל רק שני ארצות, אפשר, קוביה. אז יש לך איזושהי חלוקה שאני יכול אם אני מסתכל על הפונקציה הזאת, כאילו X מינוס 1, הפונקציה לא כאן אז אזורים ב-R, באיזה אזורים באומגה אני מקבל ואז יש לי, מתוך ההגדרה של מרחב המדגם, יש לי הסתברות לסט הזה, זאת אומרת, הסתברות ל-X שווה ל-X1, זה בעצם ההסתברות של זה בעצם ההסתברות במרחב המדגם של אומגה 1. אומגה 1 זה f במינוס 1 של x. וכן הלאה. אז אני יכול למפות סדרת המסתערת במרחב המדגם. והדבר הזה מגדיר בסופו של דבר מה שאנחנו קוראים ההתפלגות של
אפשר לרשום את זה אנוטציה.
היא לא מוזרה, היא קצת חסכונית, אם תרצה. אתה תתייחס לרגע לזה. זה יהיה מאוד חשוב. מה שאתה אומר מאוד נכון, פעם שנייה פה שתובר לי את זה שאני חשבתי.
לא, אבל כאילו מה זה
מה שהייתם כאילו בפיזיקאי, אני נורא מצטער לך, לא עושים את זה, לא עושים חלק בכלל.
גם זה בעצם.
אני כן, אני יכול לחשוב על זה. הוא אומר, ראית X, תגריל אותה. ואז אני יכול לחשוב על אספי, הוא עושה מקרי, שמוגרל בתוך X. זה בדיוק הצובר מה טוב בסדרת התצפיות. בעצם מחר רגע שלי עולם, גם התצפיות הן שמשתנים מקרים מעל העולם. והפעולות הן שמשתנים מקרים מעל התצפיות. שמשתנים מעל העולם, זה בדיוק אני יכול לחשוב...
לא, אבל קיבלתי להשפעים.
אני יכול לחשוב את זה בזניסי כמו שאני עכשיו,
לא, 12 לא קיבלתי.
אני לא הולך לפרט אבל אתה צודק שבעצם מה שיש פה, מה שנקרא מידת ההסתברות של משתנה מקרי, אני כבר מסתכל עליו דרך האינדקס נטו וחברה במרחב המדגם. במרחב המדגם זה המקום שבו יש לי את האפשרות לדגום. שם יש לי איזה מנגנון אחרי שזה פקטור 2.
לא, זה לא. זה בדיוק
אז רגע, זה משהו
לא, זה לא כזה.
כן, הכוונה בזה, אבל אני אגיע אותם בזה. אז אני יחד עם כל העולם מקצר את זה.
זהו,
אנחנו עושים תיק קטן שלי, הכוונה היא המשתנה המקרי הזה קיבל את זה.
מה שמעצבן שזה באמת מעורב.
גם זה מעורב.
זה מעורב, אבל X קטן לא מעורב.
לא, אבל אני אומר, יש לי את המאורע שהוא ה-inverse function. לא, שמעתי רגע, כן, אני עובר מה-X קטן למאורעות. זה קשור לגמרי. זאת הכוונה ב-X כמאורע. זה עושה את זה מבלג גם כן. מה שחשוב שזה שיש שני סוגי שביעות. אחת, השביעה היא תמיד תכלית לא נכונה. יש שני סוגים של החלטות לא נכונות. החלטה אחת זה לקבל את אפס בטעות, מה שאנחנו קוראים false acceptance או false positive. אמרתי שזה יהיה כאילו אפס נכון, רק חיים. אני אקבל את זה נכון. אני בוחר בטעות. false positive. אני אמרתי שזה פוזיטיב וקיים אותי, זה אומר שבעצם הייתי כאילו נכון? ולכן אני צריך לעשות אינטגרל על ההסתברות שלי אותו דבר השני, call everyone back. I just hope that the battery will hold. אנחנו ממשיכים. So again, before we continue, I got some questions during the break, which are actually very important. I really want you to ask me questions because then I understand what the difficulties is. So I want to make sure that you understand not only the notation, which is sometimes simplified. So for example, whenever I write something like this, p of x given omega, what does it actually mean? So again, I say it once and then never say it again. It means that the random variable x, what is the probability that the random variable x has actually a specific value, little x, conditioned on the state of the world. Now, again, I just want to remind you, a random variable was a function from the sample space. So there was to the reals, let's say. It can be also complex or integers or whatever you want. And this function, let's say that it is discrete and has some finite value, essentially is inducing a partition of the sample space, okay? So for example, if I am thinking about a die, has 6 possible outcomes. So this is the probability. So it's a function that from subsets of omega, or from omega to the 1 to 6 numbers. So there is an inverse map. What part of omega gives me 1? What part of omega gives me 2? What part of omega? So this is where I actually do the samples. And of course, the probability of this subset is going to determine this probability. I mean, so again, in principle, what you should do is always go back to the sample space. In the sample space, this is the only place I actually have a mechanism of random sampling. There I can draw points at random if you want to think about random samples. And so this random, or the probability of any subset, is going to determine eventually the probability of the random variable to get a value. And this is what I mean by p of x. So it's a bit confusing, but you get used to it. So p of x, essentially what you have to do is really always map it back to the sample space and see how it partitions the sample space. Of course, again, for the mathematicians here, in the continuous case, it's a bit, you have to be a little more careful because this inverse map may lead you to something which is not measurable and all sorts of ugly things like this, but we really don't care about this. Okay, so we always assume that this inverse map exists and we can actually sample the inverse map of the variable. Okay, this is one thing. The other thing is, of course, that I used in this simple proof of the Neyman-Pearson lemma, I used, of course, what I proved already about the Bayesian optima. So again, the proof was we selected a specific prior, given theta, we choose this prior, and then we use what we proved about Bayes with this prior. And this gave us this relationship that the sum of errors in the theta is always smaller than the weighted error with the same priors of any other decision. This was using this. And then we got what we wanted in the Neyman-Pearson. Okay. So now we really want to extend it to the case of multiple observations in a little more interesting way. So first of all, okay, so this was just something I want you all to notice, that conditional independence doesn't mean independence. Usually they always contradict each other. So when you say independence, you actually have to specify independence under what, or conditions on what. So now, before I go on with analyzing the properties of this thing in the large N limit, as I already started to mention last time, I just want to write down Bayes' formula again for this case of multiple observations. Okay, so simply Bayes' rule. Nothing more than that. If I, in the case of a binary of simple decision, okay? Omega is just a sum of two. So the probability of omega 1, let's say, given my sample, IID sample, what is it? So of course this is in this case, a probability between 0 and 1, but simply using Bayes' rule is the probability of P1 given the likelihood, divided by what? So again, I use the complete or the total probability sum. So this is P of omega 1, P of xn given omega 1, plus P of omega 2 given xn of this. Okay? So this is nothing more than Bayes' rule. When I explicitly wrote, this is P of xn. All of this. Okay? And you see it's a sum of two products. Sum of products are not products. Okay? Now, just one line. So this is, I'm just continuing here. This is the ratio, this ratio, P of omega 1 times the product divided by P of omega 1 times the same product. Omega 1 plus P of omega 2 nothing here. But now I can divide by the numerator. Okay, so I can write it like this. This is 1 over 1 plus divided by the numerator, so it's going to be P omega 2 over P omega 1, the product. Product of what? This divided by this, so P of xi over omega 2 divided by P of xi over omega 1. Okay? Nothing is wrong here, except maybe the assumption that it is not 0. If none of them is 0, then I can do this. Okay? But this is nice. Why is it nice? So I'm going to do something which again looks stupid, maybe. I'm going to write it as 1 over 1 plus, and I want to put all of this in the exponent. Okay? So I want to write it as e to the minus something. And we'll see in a few minutes why is it interesting to write it like this. So what's going to be here? So it's going to be the sum I go to 1 to n of log P of xi omega 1, P of xi omega 2. So this is simply the log of this product. Okay? The log of the product is the sum of the logs. Okay? And of course, I need to add here, or subtract if I want. Write it as a minus here. Log of P omega 2 divided by P omega 1. Okay? So this looks like a silly rewriting of the probability. But for those of you who know something about neural networks, if we define the function, the sigmoid function, which is, let's call it psi of x equals 1 over 1 plus e to the minus x. So how is this function over the reals? X is the real. How is this function looks like? So what is where x goes to infinity, what is it? This will go to 0, and the whole thing goes to 1. For x equals 0, what is it? Half. Okay? And for x goes to minus infinity? 0. Okay, so this is a function that we really like both in neural network theory and then, let's say 1 is here somewhere, it doesn't really matter. So it's a function that goes from 0 to 1. Of course, it should go from 0 to 1 because it was a probability, depending on x. And where x is very large in some sense, if it's going very quickly from negative to positive, this will be very steep. Okay. Actually, so the whole interesting part is really here. The slope here is 1, as you can easily. Actually, the derivative of this function is simply x minus 1 minus the function. The function times 1 minus the function is the derivative. That you can check for yourself. Okay, so this is called the sigmoid function. In neural networks, we really like this function because it's a continuous version of a threshold. Okay? In some sense, it's 1 for very big x, it's 0 for very small x, and it gradually goes between them. Continuous version, differentiable, we can take derivatives very easily, and so on and so forth. So this is called the sigmoid function. How many of you haven't seen this one before? Anywhere? All of you. Okay, all of you saw it before, almost. Okay, so now what we actually call a perceptron. This is something which, the simplest neural network, which you call the perceptron. So the perceptron is essentially a neuron, a formal neuron, that has the following structure. So we have inputs. It was actually written here on the board before I came, so somebody's talking about it. Maybe Johan. So they're inputs. Let's call them x1, x2, x3, and so on, up to xn. Okay, so these are some sort of input nodes. These input nodes, in my case, are going to mimic the fact that x is observed. We'll see in a minute. And this is the output node, which may call it y or psi, which is usually defined as the sigmoid function. This psi, sometimes called a sigmoid, simply like this. It's the same thing. So it's the sigmoid function of what? So it's the sigmoid of the sum of some weights, wi, xi, minus some threshold. This particular function, so everybody see it? Maybe my handwriting is again terrible, but so this is called the perceptron. So strictly speaking, we may replace this sigmoid by the sine function, which means actually usually I really interested only in 0 up till 0 and 1 after 0. It's not really the sine, it's the 0, 1 function, the theta function. But the sigmoid is actually a nice smooth version of the sine, if you want. So if it was a sine here, they put an n, it will be just plus. Actually, it can be plus or minus 1, or I can shift it, and it can be 0, 1. It can be an arctangent, it can be something similar to this. Actually, these are all the same functions. But the question is, what is the connection then between the base rule and the sigmoid? So imagine now that the sigmoid actually has observations here which are identically independently drawn from some space. And we'll give you an example of this for the exercise in a few minutes. I mean, so this can be, for example, letters in text drawn independently from a text. So you have, let's say, a text written in alphabet of 26 letters, A to Z or something like this, and I can independently draw letters from the text. And now I want to make a decision about the text, or I want to actually ask the question, what is the probability that I'm in a certain world, let's say the text is in English, or in another world, the text is in French? Or forget about the fact that French has slightly different alphabet. But okay, so let's say that they're all the same alphabet, and I want to make a decision like this, and this is precisely the exercise you're going to do at home, which I think Noga already sent you. So I want to make a decision about the text, which is essentially, so I'm playing this game of independently drawing letters from the text. And essentially what I'm going to give here is the number of times a certain letters appear in my text. The number of A's, the number of B, the number of C, and so on. So you can think about X here as the number of occurrences of a letter. And then, let's say that I want to make an optimal Bayesian calculation, which means I actually want to calculate this probability. Then what Bayes' rule is telling me, take the weighted average of your inputs, but the weight should be what? So let's say that this was the sum over the sample. Okay? Remember, I'm talking about a large sample. I can change it into a sum over the letters, just replacing each term with the number of times this letter appears in the sample. Is this clear? So I can actually replace this by the sum over all possible x's. Let's say that it's finite in discrete. And here write the number of occurrence of xi in the text, or in the sample, times this. Or maybe not write xi here because it's confusing. Okay, and of course this is some sort of a threshold again. So notice the similarity. I mean, the threshold goes to the log prior ratio. And the sum goes to this, if I understand correctly the notion of visualization. So the x's here actually should go to the number of time x appears in the sample. And the w, what should be the w? In order for this network to be optimal, to be really the base calculation. So w I should simply be this log likelihood ratio. Okay. So here is a perceptron. A perceptron. This is a perceptron for any practical sense, where I specifically choose the weights to be these numbers. If I choose the weights to be positive or negative according to these numbers, then a perceptron is doing exactly the Bayes calculation. Okay, so this is good news for all the neural network people. In some sense, what they play with neural networks, I mean, based on some analogy with the neuron, is actually a very well-defined mathematical concept. It's just calculating the Bayes probability of the class. Okay, so in principle, any hypothesis testing or any binary decision that is made on conditionally independent observations can be solved optimally by a neuron or a perceptron, a one-layer perceptron. So why do I need more than that? I mean, why do I need more than one layer in the real world? Let's say the word is binary. Well, I'm still talking about simple decisions. If you want to go beyond simple decision, we'll binarize it. We'll make a sequence of binary decisions in some sense. And I can always do that, and we'll come back to this later on. You can always encode things in terms of binary decisions. So this is not what I want. But why is one layer perceptron should be enough? I mean, here are the weights. I simply have to estimate them somehow, learn them somehow from the data. Of course, in order to learn them from the data, I need some estimates of these probabilities, which is going to be a tricky thing, as we're going to see later on. But in principle, here are the weights. If I just define the weights to be these log likelihood ratios, then a perceptron is actually making the optimal decision for me. The reason why one layer is not enough is actually because usually our observations are not independent. I'll just give you a classical example. Let's say that you have an image, and you have to make a decision if this is a face or not a face, something like this. Okay? So what should you do according to this? You have to look at the statistics of, let's say, pixels in the image for faces, and then the statistics of pixels in the image for not faces. This will be the probability given the assumption this is face. This will be the pixels given the assumption it's not face. As you're already going to see, single pixels are really problematic here because there's very little difference in terms of the probability, let's say, of a pixel being black or white or something, or gray or whatever level can be there, or color, or whatever it is. This is exactly what I mean by independent. And then if the pixels were conditionally independent on this assumption face not face, then I could simply take one big perceptron looking at all the pixels and make a binary decision, and that's it. What is the problem? Images, as you all know, the pixels are not really independent. I mean, there's very strong correlation between adjacent pixels in images. So I cannot make this assumption. So essentially, all the usage of multi-layers here has exactly one goal: to make the features more and more independent. Not only more and more independent, also preserve the information that I really want. So they should do two things. One is to throw away unnecessary things, I mean, compress in some sense, and we'll come back to this later on. And the other thing is to make them as independent as possible. And only after doing this, I can take a perceptron and essentially play this game. So remember this. This is precisely the motivation for using multi-layer networks for making decisions. We need more layers because we need to get rid of unnecessary information on one hand, and then make them independent as possible on the other hand. Okay, we'll come back to this. So this is just a simple connection that you all should know between Bayes' rule and perceptrons. Any questions about it? No. Okay. So now I want to continue from here. So everything I said so far was what we call decision or batch decision. I mean, I decide on all the data at once. Okay, so I get the sample. The likelihood ratio test tells me, look at the likelihood ratio. This is the best thing you can do. We'll actually, later on, we'll call this likelihood. You see, this is likelihood ratio. This one number, the likelihood ratio, is really compressing for us the sample in some sense. It's really giving us everything we need to know about the sample in order to make the decision. But it's actually quite remarkable. There was a big sample, maybe a very big sample, and then we essentially compressed it to one number, this likelihood ratio, and this one number was enough for us to make the decision in an optimal way. It's quite remarkable. We'll generalize this concept later on to something which we call sufficient statistic. I mean, this is some function of the data which summarizes everything we need to know about the data in order to make the decision. So notice that something non-trivial happened here. When we have a lot of observations, this particular product, or this sum of log product, sum of log ratios, is really everything we need to know. But before doing that, I want to ask, how is this thing behaving for very large samples? So what is the behavior of the likelihood ratio when n is very large? Okay, so this is, again, an example, maybe the first example of this course of some sort of asymptotic analysis, which we are going to repeat again and again. It's going to be very, very important in the end. So how is this behaving? So I said already, first of all, notice that this thing, the log of p of xi given omega 1 divided by p of xi given omega 2, these are, let's call them, just for the notation today, we call them zi. Okay, so zi are also in the IID numbers. They're independent and identically distributed numbers, variables. Why? Because xi was independently and identically. It was independently drawn from either one, omega 1 or omega 2. So for both of these things, these are independent. So these are also IID. I'll keep it aside for a second, asking what is the distribution of zi. We'll come back to this. It's actually asymptotically it's going to look very interesting. But what is important for me. This is an IID function. So essentially, I know that this the log likelihood ratio, log of this likelihood ratio, or the log of the product. I think I'm very just to make sure that we understand. This is a sum of the log of the product, log of the ratios. So this is the sum of IID random numbers. What do we know about sums of IID? So, okay, I mentioned it to you the first class. The law of large numbers. This is really a very important thing. So we know these are IIDs. This is going to behave nicely when n goes to infinity. So what is going to be? So if I divide it by n, I look at the average of a sum of IID numbers. It's going to go to what? Just to make sure that you're all with me. The expectation. Okay? So this is going to approach the expectation over what? Over x. And you have to be careful here. You have to know with what to average, actually. It depends on where x came from, of these numbers. Okay. So this is simply the law of large numbers, if you know. The weak laws. The weak laws of large numbers. Yes. We can't change. Sorry. Okay. Okay. So this is important. So essentially, the sum of IID numbers. So this is going to get to n times the expectation. Okay, because I didn't divide by n. N times the expectation. All right. So before we continue, I want to make sure that this type of expectation, the expectation of a log ratio of two probabilities, is actually something very important. You're going to see it again and again in many, many different places. So essentially, notice here that when I mean expectation over x, it depends if x comes from omega 1 or omega 2. If x comes from omega 1, this is going to be the expectation with respect to px given omega 1. If it's x comes from omega 2, it's going to be the expression with respect to omega 2. Okay, so this number is going to go either, if x actually came from omega 1, it's going to be, this expectation is going to be with respect to x from omega 1. If x comes from omega 2, it's going to be a different expectation. So we actually like to think, so it's going to be either this distribution that averages here, or this distribution that averages. One of them. And this is not the same thing. So I'm going to define something very important. Definition. Okay, I'll just write definition as def from here on. This is something which we call the KL divergence, or the cross entropy of two distributions. We'll denote it by d KL of any two distribution, P of x, with respect to another distribution, Q of x. And I'm sure many of you have seen it before, but this is something which we really need, and I can't emphasize the importance of it. So it's the sum over all possible x of this P of x, log or ln. I'll write log. I usually mean ln. In some cases we mean log 2. In some other cases we mean other things. But when I say log, it's either ln or log 2. Okay, but usually, it doesn't matter. Okay, so this is the definition. How many of you haven't seen it before? Many of you. Okay, so this is important. So this we call this KL. Usually we omit it, but it's called the Kullback. After two people, the Kullback, Leibler divergence. And it has some very interesting, very simple proof properties that I just want to begin to show you. It's actually something which is a function that we usually call an information theoretic measure. But at this point, information theory is beyond us. But this already shows up here. And if I define this to so what is the first thing you can say about it? By the way, if x is a continuous variable, and these are actually densities, so the same thing essentially works. I just replace the sign with an integral and do it over dx. But at this point, we think about it as a discrete set, okay? Sum over x. Okay, so what is the first thing you can show or you want to show about this D? Properties of D. Notice my notation is more or less consistent. I mean, I'm going to write it as a functional of these two conditions, two different things. This is the standard way people in information theory think about it. So it's a functional of the two distributions, which means I'm actually thinking about all the possible values. It doesn't depend on x. If I want to be careful, as David wants me to be, I should write dots here, but it's not a function of x. Okay? Just a function of these two distributions. Think about it as just a two measure over the same x. Okay, so what are the things that we need to show now? There are many, many good properties for this D. One thing I want to prove now, so the claim 1, D PQ is greater or equal to 0, it's non-negative, with equality if and only if P equal Q as a distribution. Have to be careful here again. I mean, if this is a continuous distribution, then it's up to measure 0. It's quality up to a set of measure 0. Again, I'm not going to bother you with this too long, but so you have to be careful. Of course, it's some sort of an average. If it's actually an integral, then you have to be careful what I mean by this. So it may be different at points which have no mass. Okay, how do you prove this? Those who know this already, I mean, is anyone here? Why is this positive? So actually, there are many ways of thinking about it. The easiest one is there are many easy ones. If you know Jensen inequality, for example, how many of you heard about Jensen inequality? Some of you. Okay, so Jensen inequality is a property of convex functions. So you can, it follows immediately almost from Jensen. But if you don't know Jensen inequality, I'm not going to prove it right now. You can just use the notice that that ln x is less than 1 minus x. If you don't believe, if you don't know how to prove this, I'll give you a proof by a picture. Of course, not a proof, but this is ln. You all should know how ln looks like. I mean, it's 0 at 1. Okay, 0 at 1, and has this. It's above the string, so it's what we call convex function. Convex or concave? Concave function. Concave function, and x minus 1. And x minus 1 is what? So x is this function. Goes through the 0. X minus 1 goes through 1. It's the same function, x just shifted. So x minus 1 is simply the tangent of ln at the point 1. If you're not sure, make sure that the slope of ln at 1, what is it? Is 1. It's 1 over x. 1 over x, or the slope is right. Okay, so this is really the tangent here. And they both go through 1 and 0. Okay. So this is this inequality. Okay. The ln is always less than this line. Okay. With equality where? Exactly at 1. Okay. So this is very simple. I know I'm a little bit too elementary for some of you, but that's all right. So now all we do is write x as qx over px. Of course, here, okay, this is, of course, a very bad notation. Let's call this y. Okay, and this is y. just to make sure that I'm not using extra twice. It's really bad. So I just write y as this. So what comes out of that is that ln y, which is ln qx over px. Of course, I assumed here that px is not 0. Is less or equal than, well, none of them is 0, okay, for that matter, is less or equal than what? Than qx over px minus 1, okay? So now I multiply everything by px. So I take, so px ln qx over px is less or equal than qx minus px. Okay, what I did is simply multiply this by px. Okay? But now I sum. Okay? So I take this and then sum over x. I know that when I write it like this, it's hard to follow, but this is simply, okay, I multiply this by px and sum. But now what do I know? This is going to be minus the d pq by my definition. Why minus? The argument in the log is reversed, okay? So log of 1 over x is minus log x. And this is going to be what? Sum over this distribution minus sum over this distribution, but the distributions are summed to 1. Okay? So this is going to be less than 0 because the two distributions are normalized. Okay? Okay, so now just reverse the sign and you get what you want. Okay, so or dpq is greater or equal to 0. With equality when? Precisely when there is equality here or here, which means that the y is 1. So if the y is 1, it's exactly about p equal q. Otherwise, it's not. It's going to get it. Okay, so this is a simple proof of this statement. Now this is important. Let's keep it in mind. There are many, many other properties of this d that we are going to discover slowly. One of them, but the first thing to notice is that it's not symmetric in P and Q. Okay? So the dpq is very different, of course, than dqp. Remember this. Both of them are positive or not negative, but they're very different functions. And they're going to be related directly to our two types of error in a second. In 5 minutes, I hope. All right. So now, if this is, so this, let's go back to this limit. So this limit, if after noticing this definition of KL divergence, what is this going to look like? So again, the log likelihood ratio is going now. I'm going to, where n goes to infinity, is going to behave like what? Like n times the d between px given omega 1 and px given omega 2, if x actually coming from omega 1. Okay? Is this clear? So actually average x was actually sampled from this, and it's going to be minus n the d of the other side, p of x given omega 2 to p of x given omega 1 if x comes from the other distribution. Sorry for writing it on the slide here. It's a bit problematic. Okay, so you notice that the log likelihood ratio is going to be to limit some sort of a linear function in n, where the slope of this linear function is asymptotically just this cross entropy or KL divergence. We all in the definition I should call it. Usually I omit this KL. Some people just denote it by KL of. Some other people call it cross entropy between P and Q, or relative entropy, or many other things which at this point doesn't make any sense, don't make any sense. So I will, at this point, just call it D, but some of you already know that this is related or very close to a measure that in Yoram's course, for example, he called the entropy. So it's actually going to lead us very closely, very quickly to information theoretic measures. Okay, so this is interesting, because in some sense we know that this likelihood ratio is going to increase asymptotically linearly with n. So what does this mean in terms of learning, making the decision? Which means this thing is actually going to rise, if we're in the first state of the world, it's going to eventually rise linearly with this slope. If we are in the other state of the world, it's going to decrease linearly because of the minus sign with the other slope. Okay, so this is nice because it's actually telling you really maybe begin to see that there's something in this D which tells essentially how much it's going to increase on average for one more example. So any more example is going to raise it by the average of exactly this D. So you see that this D has some value of information in some very intuitive sense that we at this point don't really define. So I just want to sketch it in some sort of a picture, because we really need to talk about decision making, sequential decision making. So if I actually, this is now going to be the number of examples, sample size. And here I'm going to write this log L of xn. So how is it going to behave? So essentially what I just said, every new example is going to either increase it if I'm in the first case, or decrease it if I'm in the second case, okay? But since these are random variables, you never know exactly what to do. Maybe you see a very unlikely case for one, so it's going to be noisy. It's going to have fluctuations, and we're going to talk about these fluctuations much more carefully eventually. So it's going to do something noisy like that. But on average, if x comes from P1, let's make it simple, and so it's going to increase where the slope on average is going to be exactly D. Okay. So the slope of this fluctuation, of this noisy curve, is going to be precisely this D. Let's call it 1, 2. The D1, 2 is between P1 and P2. Okay. Of the two probabilities that P of x given omega 1 and P of x given omega 2. It's a log likelihood ratio. Okay. Everything. This should be clear. So because I should throw this here. Yeah, so I saw that this likelihood ratio actually behaves like n times this expectation, and this expectation is going to behave like either the first KL or the second KL. Okay, depending on where my